Welcome back, everybody. All right. Any questions? Comments, concerns? All right, let me make sure I got my phone off here. Give me a second. All right, so let us continue then. We'll finish up chapter 10, and then the next chapter, number 11, we'll probably get that one knocked out too, because it's a very short chapter. I think there's 10, 11 slides in that one. Okay, so we'll get that finished up. All right, let's continue with where we left off. We've been talking about the different types of chemical reactions. Okay, let me back it up here. We are now talking about, we had talked about this type of reaction, which is a double displacement reaction. Now, notice something here. When you see that reaction, you see zinc nitrate, and then you have sodium. Okay. Notice in a single, did I say double? I meant to say single replacement. Notice in the single replacement reaction, you'll always have an element, a metal all by itself. And the idea is that metal going to replace this metal that's in ionic form. Okay, this is ionic form. This is a compound. Obviously, this is an elemental form. It is an element. Now, the driving force here is this. Between these two metals, which is sodium versus zinc, regardless of what physical state they're in, the driving force is which metal is more reactive. Okay, point number one. Point number two is the most reactive metal, it's going to want to be driven, wants to go into the most standard state, which is the ionic form. Okay, and so we compare sodium versus zinc. We look at the activity series. We find sodium there, there's zinc. So obviously, sodium is much more reactive than the zinc. And then you ask the next question, okay, is the most reactive metal in ionic form? And that's based on the equation that you're given, or the equation that could be written out in words, and you have to put it into an equation. And here you can see that no, the most reactive metal here, sodium, is in elemental form. That being the case, then we have yes on the reaction. And we just simply exchange places with respect to the metals. Zinc would then go into the elemental form, okay? And then sodium will replace the position of where zinc was, but before you put them together, you write them in ionic form first so you can put them together in the correct number, in the correct ratio. Fortunately here, zinc plus is a plus because it's a group 1 metal, has 1 valence electron. And then nitrate, nothing's happening to nitrate. Notice nitrate just going along for the ride, so to speak, okay? It is the counter ion. Anytime you have a positive ion any place, you've got to have a counter ion. You won't have an isolated ion just sitting there all by itself. You always have the yin and the yang, if you will. There's where you see a plus, there's got to be a negative someplace. So we put them together in ionic form so we can then put them together in the correct formula, okay? So we went through that scenario and we found out that, yes, zinc, as I stated, is the least reactive metal. It gets converted back to the elemental form, and this is where you got to remember what its physical state would be, and obviously it's going to be a solid. You know, you got a good chance it's going to be a solid because, you know, there's only 2 liquids, 12 gases, and the rest are solids with respect to the elements, okay? Silver nitrate, excuse me, sodium nitrate, we know is soluble because of the solubility rules. Notice here we're pulling the information from everything we talked about so far, okay? The nitrates, if you look at the solubility table, all nitrates are soluble, regardless of what the cation is. Hence, that's why it's AQ, aqueous solution. Okay. All right. And then we balance it up. And the thing about balancing, in this scenario, with respect to signal replacement, and also double replacement, you're going to find that you're going to have polyatomic ions. So my suggestion to you with respect to balancing this reaction is to follow the polyatomic ions. You follow those, you like over here, you can see I got, you have 2 nitrates right there. Well, as I follow them, that means I got to put 2 on the product side to give me 2 nitrates, okay? And you'll see that that just falls, everything else just falls into place. All right, so let's go to this one here. Now, obviously, this is sodium nitrate with 2 nitrates wouldn't be the correct formula because we know, or we should know, that sodium is a group 1 element and it only has 1 valence electron. It's only going to lose 1 electron, so it always has a +1 charge. The way it's written there suggests that sodium has a +2, okay, which is not correct. All right, so here we have strontium, bromide, and aluminum. So we do the same process. We're going to compare strontium at number 1 versus aluminum, regardless of what physical state they're in. We're just comparing metal to metal. So we go to the activity series. We see strontium sitting right there. Aluminum is right there. So that tells us that strontium is much more reactive than aluminum. Okay. Step number 3. Okay. Is strontium, which is the most reactive metal, is it ionic in the equation? And look what we got here. Yes, strontium is in ionic form. Okay, therefore you get a yes for that question. Therefore, NR, which means no reaction. Okay, no reaction because strontium is the most reactive metal compared to aluminum, and being the most reactive metal, its driving force is to be in ionic form. It is not, it is already in ionic form, so therefore it's not going to react any further. No reaction. But guess what? When you get a no reaction the way it's written, you get a yes reaction written the opposite. So what does that mean? Okay, let's exchange places. Let's start off with aluminum bromide, and we are reacting that with the strontium metal. Okay, same questions are asked. Strontium in this scenario is not in ionic form, so yes, you get a reaction. So you generate aluminum plus, in this case, strontium bromide. I'll let you balance them out. Okay, so you get a reaction when it's the when the metals are in opposite state. Okay, so NR up here when you're dealing with the ion, yes when you're dealing with strontium, the element. All right. Now, this is a little bit different because, right now if you look at the reactions, we are dealing with metal and metal, right? You might think, oh, we got metal, metal, but then all of a sudden what happens is, whoa, we got HCl, we got hydrogen. So how does that work? Remember, the activity series is relative to hydrogen gas, okay? Notice down here in the activity series. Okay, when this activity series was put together, they were using as a reference point hydrogen gas. And so everything's really relative to hydrogen with respect to reactivity. And earlier before, I said that these in BODE very reactive with water, extremely reactive, okay? And so these I'm going to list as Bm prime that represents the metals from lithium to sodium. When they react with water, which is one of the forms of hydrogen, because you got hydrogen in form of H2O, it will react to give us the metal hydroxide plus hydrogen gas. Okay. In fact, if you took any of those metals, lithium through sodium, you dump them in water, the reaction gets very vigorous. It produces heat and a lot of hydrogen gas, a lot of bubbling going on. And if it gets too hot, it will ignite, okay, on the surface of the water. But if you check the pH of that solution when you're done, you will find it to be alkaline because hydroxide ion has been generated, okay? Now for the other ones from magnesium through lead, which I'm going to designate as M double prime, okay? They require a little bit more vigorous conditions for them to react. They will not react spontaneously with water, but they will react with acid. And an acid could be, I'm going to just tell it HX, any acid available, it will react. What it does, it will then create the metal double prime X, the salt, plus hydrogen gas again, okay? And those are for the metals that I've designated as M double prime. These down here are designated as M single prime, okay? And if we look at, ask the question, let's start with the hydrogen here. If we say if metal double prime is more reactive than hydrogen, okay, so we look for the metal double prime or any metal that's more, you can see that any metal below lead is more reactive than hydrogen, okay? But depending on their position, it will require either an acid like HX or water if it's one of those reactive ones, okay? And so the quote ionic form of hydrogen could be either in the form of water or photon, okay? And so in this case, you can see here that any of these metals will react with either water or an acid to generate the hydrogen gas. The other metals, if you ask that same question, and those are the metals from copper to gold, ask the question, you see that hydrogen is more reactive than I'll call these metals triple prime. Hydrogen is more reactive than these metals. And if I were to put these metals in the presence of either an acid or water, you get no reaction because hydrogen is already in the most stable form, and that is ionic in the form of either a proton or in stable water, okay? It just got to remember that the ones that are not in bold require a little bit more strength, and it's like an acid for them to react. Not to say that copper, silver, mercury, and gold do not react. They will, but they require extremely more vigorous and more acidic conditions. But we're not gonna go into those. They just say unreactive with respect to hydrogen. All right, so that being the case, you see aluminum and hydrogen. And so if you look for aluminum, and here's hydrogen, okay? Same question, who's more reactive? Who's more reactive? Well, looking at the activity series, aluminum is a lot more reactive than hydrogen. Aluminum is more reactive than, I'm just going to say H in parentheses, okay? And then the second question is, all right, is the most reactive reactant here, in this case, we can't say it's metal because we're comparing with hydrogen, is the most reactive one in ionic form? The answer is no, okay? And therefore, number 3 says yes on reaction, okay? So here's the most reactive form. It is not in ionic form, so we get a reaction. And we're going to generate H2 gas, okay? And the salt. So the aluminum is going to replace the hydrogen, just like we did with the other metals. And in this case, we're going to put them in ionic form first, because we know that aluminum is a +3 metal ion. Okay, it's in group 3. And we know that chlorides here are -1. They're group 7. We need 3 of them. So therefore, the formula for aluminum chloride will be aluminum Cl3. Okay, so there are your products. And now it's a matter of you balancing them. Let me clear this up a little bit. Okay, and there's the reaction. Now we put the physical states. We know hydrogen gas is a gas, obviously. And aluminum chloride, based on the solubility rules, that chlorides are soluble. Aluminum chloride, there's only three examples of chlorides that are not soluble, and that is silver, mercury, and lead. Okay, so AlCl3 is aqueous. And we got the reaction. And here we can do, to balance it, well, we can do a number of things. I don't know, whichever one you feel comfortable with. I will go with the chlorides. I'm gonna, let's see, we can do this. All right. Couple ways to do this. Now, this was almost a trial and error, but I can focus on the hydrogens. But let's tell you what, I got 3 chlorides here and only 1 there. What if I put 3 there? Okay. Well, that balances my hydrogens, but it kind of messes up balances my chlorides, does it not? But it kind of messes up my hydrogens, okay? Because now I got 3 hydrogens on the left, and I got 2 on the right. So I get a disparity here. So what if I make it with, I don't know, let's try 6 hydrogens, or 3. Oops. What if I put 3 hydrogens on the right and change that 3 to 6? Would that work? Okay, then my hydrogens get balanced and I'm good, but it kicked up my chlorides. All right, what if I put a 2 in front of my aluminum chloride? Now my chlorides are happy, but it kicked up my aluminum. No big deal. I put a 2 there. Okay. Is that reasonable? Does that look balanced to you guys? It certainly does. I think so. Yeah, there we go. Okay, so that one took a little bit of trial and error. Okay, what if we could have gone either that. We went with the hydrogens, but we could have gone with the chlorides. Okay, or vice versa, whichever one works for you. All right, so with respect to single replacement reactions, little flow chart here to help you out with respect to first determine if the reaction is going to proceed. It says determine the most reactive metal. If you're comparing with hydrogen, either in the form of an acid or water, then that should really read most reactive metal / hydrogen or water. Okay. And once you determine which is more reactive, then determine if it's in salt form, it's ionic form, then boom, no reaction. That's it. Because the most reactive metal is in the most stable state. If it's not, then yes, you get a reaction that proceeds, okay? And you just simply exchange single replacements, exchange the metals or exchange the metal and the hydrogen. All right, which brings us to, I believe, the last reaction. This is called double replacement. Notice the first one, the one we just got done, is called single replacement. Here, it's a double replacement. Nothing complicated, really. Let's walk it through. First of all, I have an aqueous ionic compound. Everybody's ionic here. Okay. We have an AX ionic compound, which is soluble. And then we have a BY ionic compound, which is also soluble. Okay. Now, what happens is they simply just exchange partners. And so AX now becomes AY, and BY now becomes BX. Okay. The anions and cations have just exchanged places. Now, what drives this reaction is whether the products AY and BX are either soluble or not based on the solubility rules table. Okay. In order to have a positive reaction, one of these new products has to be insoluble. Basically, a precipitate falls down. We get a solid material because of its nature of the beast. It's not soluble in water and it will precipitate. It gets cloudy. Okay. And the other partner, 9 times out of 10, is soluble. The other new compound, I should say. Okay. If both new products are soluble, then no reaction. Okay. If both soluble, no reaction. Let's do a couple here. And we did one of these a few slides back last time we were here. So if a reaction proceeds, we get a solid. We call that solid a precipitate. Okay, reaction occurs in solid forms. If it does not, we get no reaction. Okay. Learn to use the solubility rules on the periodic table. And let me rehash those very quickly. Okay, on this side, we have the soluble components. Okay. Number one, any cation with those big 4, always soluble. Any acetate ion, any nitrate ion, regardless of who the metal is always soluble. And the same is true for chlorides, bromides, and iodides, always soluble, except if they are bonded with silver, mercury, and lead. Only those 3 compounds, those 3 halide compounds are insoluble. Sulfate ions, as the halides are also, everybody is soluble, except these 5 examples. If it's calcium sulfate, strontium sulfate, barium sulfate, silver sulfate, and lead sulfate. Only 5 sulfates that are insoluble, which means all the infinite number of other compounds are classified as soluble. Okay. On the other column over here, we have the insoluble. And so all the carbonates, all the carbonates, all the chromates, all the phosphates are insoluble, with the exception being that if the carbonate is bonded to anybody of the big 4, or the chromate, or the phosphate, then only those 4 are soluble. Okay. All right. The same is true for the sulfates. All sulfates are insoluble unless they too are bonded with the lithium, sodium, potassium, or ammonia. But on top of that, there's 3 more: calcium, strontium, and barium. And so there are 7 examples of sulfide compounds that are soluble, and all the 10,000 whatever other ones combinations are insoluble. Hydroxides, very same scenario. Soluble with the big four, also soluble if bonded to calcium, strontium, and barium. Okay. So again, only 7 examples of soluble hydroxide compounds, and everybody else is insoluble. All right. So refresh your memory on the solubility rules and how to interpret them. Okay, so we have a reaction. We have barium nitrate and magnesium sulfate. Okay, so step number 1, first of all, is write everything in ionic form. That way you know that you're putting them together in the correct format. All right, so we got on the left side, we got barium, which we know that is a +2 element. We will have a +2 charge. I should say group 2 element metal. And nitrates, hopefully you can pick up on this, that the nitrates are all -1, and we got 2 of them, okay? Now, magnesium, like barium, is a +2, and then the sulfates are -2. Okay, so we got everybody in ionic form. Now we simply create the new products. Okay, we're going to take the barium and now make the sulfate. And since I have them already in ionic form here, then I know what they would be as a new product. So I got Ba SO4. Okay. Now, since I have the solubility table here, I can also look up to see and determine whether it is soluble. Normally, sulfates are soluble because it's in the soluble column. However, there are 5 examples where barium sulfate is insoluble, and sure enough, right there, we got calcium, strontium, barium, silver, and lead. 5 examples there make insoluble sulfates. Barium is one of them. So that tells me right away that it's insoluble. I can put an S there. Okay. And that means also that I got a positive reaction. Now I just exchange the other 2, and that would be the magnesium with the nitrates. You can see here magnesium has a +2, nitrates have a -1. So to put them together, I need 2 nitrates. So I got magnesium, and I use a parentheses, and I got 2 of them. I need 2 of them. Effective solubility, well, number 3 of the solubility table, all nitrates are soluble. So quickly I can do AQ. Okay. All right, so step 1, put my reactants into ions so I know what their charges are. Then from that, make the new compounds by just simply exchanging partners, if you will. From there, we can determine whether the new compounds created are soluble or not based on the solubility rules. Okay, and then the next thing is simply to balance them. And here, this one is pretty self-explanatory because double displacement reactions, okay, follow the polyatomic ions. We had 2 nitrates over here. We got 2 nitrates as magnesium nitrate, so that's good. We got 1 sulfate in the beginning reactant. We got 1 sulfate as a product. 1 barium, 1 barium, 1 magnesium, 1 magnesium. Everybody's happy. We have a balanced chemical equation. All right, this particular reaction just by default just balances itself. But if not, again, follow the polyatomic ions, okay? Treat that as a unit, don't separate them. You know, you can if you want, but you know, if you got to keep track of all the oxygens and all the nitrates and all the sulfurs. You're just better out just to keep track of them as a unit. Okay. All right, let's try another one. We have potassium nitrate. Notice it's aqueous, right? Because all nitrates are soluble. Ki, which is potassium iodide, which all halides are soluble, even more so in that day. You got potassium up there, it's soluble. So both of them are correct. You know, they're both soluble and aqueous. All right, so let's break it down. Lead is a +2. How do we know that? Because nitrates are -1, and there is 2 of them. That means that lead must be a +2 species, it has to be. And then we got 2 nitrates here to work with. Okay, Ki, we know that's a +1, and the iodides are a -1. So we're going to take the lead and combine it with the iodide, which exchanging partners. Okay, we know that potassium lead is a +2, iodide's a -1, so we need 2 of them. So the formula would be K. Oh, sorry about that. Got potassium in my brain. We have lead iodide, subscript 2. Okay, let's find out if they are with the solubility of the new product, lead iodide, and specifically lead 2 iodide. So normally the halides are soluble, but if they're bonded with lead, they're insoluble, and therefore we have a solid. Okay. Then we put together the potassium and the nitrates, and it's a simply 1-to-1. So we have potassium nitrate, and we know that nitrates are always soluble. So this is its state is AQ because nitrates are soluble, and then on top of that we got potassium, which is part of the big 4 there, number 1, always soluble. Okay, so we are equation-wise, we got it together. Now let's balance it. And earlier I said, follow the polyatomic ions. We have 2 to begin with here in the beginning, right? 2 of them. But now we end up with 1 as potassium nitrate. No big deal. Put a 2 in front of potassium nitrate. That balances the nitrates. It does kick up my potassium. Okay, no problem. Put a 2 in front of Ki. That takes care of potassium. And then now I got 2 iodides. That works out because I have 2 iodides as products. And I got 1 lead. So boom, it's balanced. Okay. All right, let's try one more. We have a barium chloride, so break it down to ions. We got 2 chlorides. And then we know silver is always a +1, and the nitrates are always a -1. Okay, so we're going to take the barium and exchange it with the nitrates. And that gives me a barium nitrates, 2 of them. We get a +2 in barium, and the nitrates are -1. I need 2 of them. Check out the solubility. Nitrates are always soluble, so this one is AQ. Okay. Now we take the silver and the lead, and it's a straightforward 1-to-1. Not lead, what am I saying? Chloride. So we got silver chloride. Okay. So that is pretty cool. We're happy there. Now continue to follow the polyatomic ions. We got 2 nitrates as products. We got only 1 as reactant. So what if we put a 2 in front of silver nitrate? That balances the nitrates. What that does is that kicks up my silver. Okay, so we got to put a 2 in front of silver chloride. All right, and that's okay because that kicks up my chlorides now, but that works out because there's two chlorides to begin with barium chloride. Okay, so I got one barium and one barium on both sides, and it looks like everybody is happy now. We're all balanced up. And there's our reaction. Okay. Notice again, sometimes as a student, you don't see it. All we did for a double replacement reaction, the barium now partnered up with the nitrate and the silver partner up with the chlorides. Okay. You get silver chloride, barium nitrate. And after that, after we put them in ionic form first, so we can put them together in the right ratio of positive and negatives. After that, then we looked up the solubility of each one based on the solubility rules and determine AQ or solid. If both of the products were soluble, then we would get no reaction. Okay. Now I'm going to make one real quick. Now we'll come back to it. Okay, now what do we mean? Here's a reactions there. They're called redox reactions. Okay, this is like a general all-inclusive type of a name of reaction that encompasses a multiple of different types that we work with. For example, a single replacement reactions, combination reactions, decomposition reactions. All of these are classified under the umbrella of what we call redox reactions. Now, redox is short term for reduction and oxidation. Now, what are we talking about here? We are talking about the loss or gain of electrons. The loss of electrons is called oxidation. When a species, chemical species, loses electrons, its term is called oxidation. Okay. I don't know, sometimes if you use X to help you out, exit the building, so to speak, your electrons are being lost and they're going someplace. Okay, so that's one way to maybe help you out. When you gain electrons, now you've seen this before, right? Remember we said all metals lose electrons. We call that oxidation. All nonmetals gain electrons. Guess what we call those? Reduction. Those type of reactions. Okay. And so what is taken are the RED, the red, and the ox to generate redox reactions. Now, redox reactions, any reaction that involves the transfer of electrons occurs when there is loss of electrons someplace. There's always going to be gain of electrons someplace else. Okay, right now in your battery, if you're running off a battery in your electronic device, on one side of your battery, it is giving up electrons, while the other side of your battery is picking them up. Okay, redox reactions. So in essence, what it's telling you, a reduction is when an element's charge goes down. All right. Whereas oxidation is when the element's charge goes up. You can't have one without the other. Okay, it's all they occur simultaneously. Oxidation numbers of ions are the same as the charge. I talked about that. Okay. We know that elements all in their natural state have an oxidation number of 0. And I also stated that we use the term oxidation state or the oxidation number because that encompasses both ionic and covalent compounds. Ionic compounds, there's no question. One, you get a full negative, full positive charge. Whereas covalent compounds, you don't. You have partial charges, partial positive, partial negative. And so we're not having a full charge, we're having a partial charge. So to encompass both of these different type of elements, we use the term oxidation number, okay? The oxidation number of oxide, being in, say, potassium oxide, is a -2. The oxidation number of carbon dioxide is also a -2. So it doesn't change this oxidation number simply because it's covalent versus an ionic, okay? We've gone through this. If you haven't picked up on that, go back, make sure you get it. Group 1A, Group 2A, Group 3A, they have their respective oxidation number of 1, 2, and 3, positive 1, 2, and 3 respectively. The Group 4 elements can have either a +4 or a -2. They're on the fence. You know, the driving force again, remember, is the octet. By losing electrons, it has now fulfilled the octet, because now the next energy level where the electrons were is the next one in, and that one's full. So the octet has been fulfilled. Okay. Once we pass the group 4, now we start picking up electrons, and those we get into the realm of the nonmetals. So, and they're going to pick up enough electrons to fulfill the octet. So group 5 has a -3 oxidation number. Group 6 has a -2, and group 7 has a -1. Along that is a tool to help you out, okay? That when we get to group 5, 6, and 7, that also tells you how many bonds that particular element can have. For example, nitrogen, we know, is in group 5. When it becomes nitride, okay, it will pick up 3 electrons. We went through this before, right? But the additional bit of information you can get is that when nitrogen is bonded covalently with something, it will make a maximum of 3 bonds. Okay, it will make a 3-bond formula structure. Group 6, let's pick oxygen. Oxygen, as we know, when it becomes an ion, becomes oxide, it has a -2 charge. But along that, oxygen can make at the most, I'm going to put hydrogens on these to make it easier. A neutral bond, it can make 2 bonds. We know water has 2 bonds. Yes, it has lone pairs, but we're not worried about it. We're just talking about how many bonds it can make based on the group it's in. And then group 7, things like fluoride, okay, and all the halides can have a -1 charge. Well, these guys, which I'm just going to make it an X. Okay. X can only make 1 bond with hydrogen, 1 bond. Hydrofluoric acid, hydrochloric acid, 1 bond. So not only does it tell you the type of ion or anion, but that with its position in product table also gives you information as to how many bonds it can make and remain neutral in charge. Because we know that ammonium, because of a lone pair, can bond with another hydrogen, but you end up positive, okay? You remember the ammonium ion? Okay. And of course, noble gases. Then you know about the oxidation of group numbers of group 1, group 2, the sweet 16 we talked about. They include silver, aluminum, zinc, and cadmium. You know, all the ones in group 1, group 2A have a +1, +2, and these additional 4. Okay, so what we can say about oxidation is this: losing electrons, the charge goes up. Okay. Now, notice something here. Pure copper has a net 0. I put a superscript 0 to designate it as the element. It has a net 0 charge, but it's a metal. and it would lose 2 electrons to become, copper 2 ion here, okay? And so what's happening here, that solid copper is oxidized. Oh. Okay. And what is being oxidized has its own little name. We call that the reducing agent. It's a reducing agent, if you will, because it is providing the electrons for other elements to gain and become reduced, okay? So what is oxidized is called the reducing agent. Now, with respect to reduction, it's gaining electrons, okay? And so from a value, mathematical value, the number goes down, right? Okay, you might say, wait, I don't understand. Well, we got 0, we got a scale here, right? 0. We got 1, 2, and 3, and down the scale, we got -1, -2, -3, right? And so when you gain electrons and you say you're maybe start at 0, I just arbitrarily say 0, and you gain electrons, okay, your number goes down. Now you can be a +3, +2, or +1, and you can gain electrons and that number goes down. If you start at 0, your number goes down, right, to the negative realm. So your charge or your oxidation number goes down when you gain electrons. Here we have sulfur with a 0, and now its number becomes a -2. So it went down here, -2 value from 0. Okay, so the charge oxidation number goes down by gaining 2 electrons. Notice in oxidation, electrons are a product of the reaction. In reduction, electrons are a reactant. It's to the left of the arrow. And we create the sulfide, okay? So sulfur is reduced, its oxidation number is decreased, and what is being reduced is called the oxidizing agent, okay? So what is being oxidized is the reduction agent. What is being reduced is called the oxidizing agent. Okay, they occur simultaneously. And if you look at a reaction, it's being asking you, okay, what is reduced and what is oxidized? What the answer is, well, that's the whole molecule. The whole molecule could be a whole molecule of some compound, or it could be an ion. Okay, so whatever is reduced, if it shows you an ion, then obviously what is reduced is that ion. What is oxidized, vice versa. If it shows you a molecule, then you have to show it to be the whole compound. For example, let's take these. Now notice these are just ions right now, okay? So let's break it down here. We got copper 2, okay? And it goes from copper 2 to copper 0. Okay, so let's think about that in that scale. Here's 0. We got 1, 2, 1 and 2. This is plus. Okay, so starting at +2 is going to go down to 0. So in order to do that, does it gain or lose electrons? Okay. I mean, how do I make a +0, a +2 go to 0? Well, you add a -2, right? And what is negative is the electrons. So copper 2 goes from +2 to 0, so its charge goes down value-wise, so it is reduced, okay? Iron starts at 0 and then ends up as +2. This is analogous to single replacement reactions if you think about it. okay? Because it could be copper 2 chloride reacting with iron to give us iron 2 chloride and copper metal. Okay? And so what is oxidized here is the iron. What is reduced is the ion, in this case an ion, because they're showing you copper 2 plus 2. But it could have been copper plus 2 chloride, okay? And we would answer the whole molecule. The reducing agent is copper 2 ion, and the oxidizing agent is copper 2 ion, and the reducing agent is iron itself, okay? Well, here's an example. This is a compound that is utilized a lot for cancer treatment, the platinum species, and it's created by taking cobalt nitrate, specifically cobalt 3 nitrate, and treating it with platinum. Okay, very expensive metal. That's why this treatment can be very expensive. All right, now, so you can see that cobalt went from a +3 to a 0 oxidation state. Platinum starts off at 0 and then goes to platinum 3 nitrate. So it went from 0 to a +3. Okay. And what is being oxidized is the platinum. What is being reduced here is the whole compound. Notice the previous example, we just had an ion, but here we got the whole compound to be cobalt 3 nitrate. So the reducing agent is cobalt, oxidizing agent is cobalt 3 nitrate, and the reducing agent is a platinum. Okay. And again, this is the species utilized. There are a variety of different types of plant species that's utilized in cancer treatment. All right. I think we got some more. Okay, there's the cobalt 3 nitrate. All right, there are videos, not only these that we record here, but of course, Dr. Kim's videos on the course website to give you some more information, a different way of presenting this information. So, don't forget about those, okay? Summary, know how to use the solubility rules, know how to use the activity series, okay? Do you have to memorize it? No, of course not. It's on the periodic table. Yes, you're allowed to use the periodic table. All right, recognize and balance the combination reactions. We talked at length about these, and decomposition reactions. Recognize the products and be able to balance a single replacement reaction, which is governed by the activity series, okay? And then a double replacement reaction, which is governed by the precipitation or the solubility rules. Okay. And then the acid-base neutralization reaction, remember that is a reaction between a proton and a hydroxide. And to balance those, follow the hydroxide, follow the protons. Okay. Combustion reaction. We're only dealing with hydrocarbons and oxygen, and the only products you get are carbon dioxide and water. Okay. And then be able to identify what is oxidized, what is reduced, and their corresponding agents in some type of redox reaction, which is, a lot of these reactions are classified as in the overall umbrella as redox reactions. Okay. All right, ladies and gentlemen, end of chapter 10. You're doing pretty good. Any questions? No questions? Because chapter 11 is extremely short, okay? And this deals with a section of chemistry, an area of chemistry called thermodynamics. And we're just giving you the tip of the iceberg. Thermodynamics is a whole big old field in itself with respect to chemistry/physics, okay? anyway, it talks about reactants and how reactants come together. We tend to think that, all right, we just take the reactant A, reactant B, like a double displacement reaction, just put them together and miraculously, things happen, reactions happen. And it's not quite there. It's not quite there. Certain things have to happen for a reaction to proceed from point A to point B, okay? So we have what's called a collision theory. Molecules, when they come together, they have to, first of all, come together with enough energy to have the reaction proceed. And they have to have the correct orientation, okay? If we look at these two reactants here, we're having two diatomic molecules coming together. And guess what? They have to come in with the correct orientation, because overall, as we look at the products, they've essentially noticed they created, a new compound. We start off with diatomic molecules and we make a compound over here, okay? And they have to come in with, like I stated, with the correct orientation and the correct or enough energy. Okay. That's what we're going to talk about. We're going to talk about all these factors that deal with the reaction that need to occur. Okay. What we have here is bonds are being broken, bonds are being made. Now, in the middle, we have this state right here. We call that the transition state. It is a point where bonds are being broken here and here, but then we have new bonds being created here and here, all occurring with the correct orientation, okay? And that is called the transition state. It's like a hybrid of the two. You're going to have properties of your products and properties of your reactants. Okay, so you're going to have sufficient collision. So what do we do to assure that we have sufficient collision? Well, the easiest thing is to increase the number of collisions, okay? And that can be done in multiple ways. Think about it is these what do you call these bumper cars that you have? You're out there in the field, you got this bumper cars. So if there's only two of you out there, not too many bumping going on, right? But let's say you had a gigantic facility and you had about 100 bumper cars. And now we're talking, you got a good opportunity for the cars to come in and bump each other in the correct orientation, correct energy. So you can, so something can happen. And so we have to increase the number of collisions, and we can do that by adding more material, for one, okay? Second of all, what's happening here, when these reactants come together, they have to have a sufficient amount of energy. That energy is called the activation energy. That is the energy, minimum amount of energy needed for reactants to become products, okay? If you don't have that minimum amount of energy, you will not become products. We designate that with the letter E subscript A to show that's the energy of activation. Molecules obviously have to be orientated correctly. I think of shooting pool. If you want trying to make you got the cue ball and you're trying to make a ball down in the corner someplace, side pocket, a difficult shot, you got to have the right. Think about it. This whole thing has to be analogous to shooting pool, or billiards, or whatever you want to call them. But if I want to make a ball in a corner pocket, I got to hit it with the right angle. That's the correct orientation. Not only that, I got to hit it with the right amount of force or energy. because if I don't hit it hard enough, it's not going to make it to the corner pocket. If I hit it too hard, it's going to shoot and jump out of the pocket. Okay. And so a lot of variables have to come into play here. All right. So correct orientation, correct amount of energy. Okay. We can increase the rate, more collisions. And what do? A simple thing is just to heat them up. Right. If we have a reaction and for some reason this reaction is taking hours, well, the simplest thing we can do is just to fire it up a little bit. It's been shown that about every 10 degrees of increased temperature increases the rate of a reaction. It's how fast this thing. So you can double the rate with a 10-degree increase in temperature. However, you got to be careful because increasing the heat sometimes actually can destroy some of your reactants. So you got to play with the numbers, so to speak. Okay. So it's not a simple thing. I wish it was that you want to make a compound and just put them together and voila, there it goes. So you gotta, maybe heat it up a little bit, add a little more energy, heat, add more molecules, okay? Or you can add a catalyst, okay? The catalyst is used quite a bit in chemical reactions. And what that does, it simply reduces the energy of activation. All reactions have this energy of activation, minimum amount of energy necessary to become product. And a catalyst will reduce the energy of activation and allow that reaction to occur, say, at a lower temperature. Or, the thing about catalysts, that could be dangerous. I had a reaction that exploded. I just happened to just step away. I took some reactants. I put them in sealed tubes, and we put the tubes in a constant bath, temperature bath, so we can pull a tube out and analyze it over a period of time. As I finished doing all the tubes, I sealed them up, and I put them in the water bath. I took one step back, and the whole thing went boom. It turns out that there was trace amounts of iron. A lot of metals are good catalysts. And that amount of metal, because I missed a step in cleaning my glassware to make sure metals were out. There were trace amounts of metal, and it caused that reaction to proceed very quickly. So catalysts can be good, could be dangerous, so you be careful. Okay. Now, as I stated, the activation energy is the minimum amount of energy needed for reactants to become products. All right. Now, we have also what are called equilibrium reactions, and these are reactions with double arrows. Basically just telling you, we here got an example of general terms. A plus B react in the forward direction to give us two new products, C and D. But you can also have C and D react to go back and go back to the A and B state. And it's an equilibrium reaction. Very analogous to those compounds that are insoluble. Remember, we classify them with some ions in solution, but the bulk of it's still together. This is analogous to that. But in essence, the takeaway here is that the rate of the forward reaction equals the rate of the reverse reaction. Classic example of this, if you take a soda pop, seal it up, you got it sealed, shake it up. You have erupted the equilibrium between the gas on the airspace and the liquid. But if you let that bottle sit there, it goes back to normal state. That gas that was forced into the airspace goes back into the liquid, and you go back to your equilibrium that it was before you shook up the bottle. Okay, it's a good example. Now, we're introducing you to these diagrams to designate the different type of reactions that we have. Okay, so what are these diagrams? Well, we can do it this way. On the y-axis in this direction, we have energy units, and for right now, they're just arbitrary energy units. Okay. And what we can do is if we follow a reaction over a given time period, we can depict that reaction at a given point, and it would have a given amount of energy, okay? And the result is this, that over collecting data points over a given time period, we can make a graph that would look like, I don't know, something like this. We have a hill, and then it'll come down, and then we got this. All right, so over here is where the reactants began, okay? And over here, I'm gonna designate that as R for reactants. And then when the reaction's all done, at some level, we have P, and that is where the products ended up with respect to their energy state, okay? Now notice that we can do, since we have a scale, we can extrapolate, just take a ruler and go dot, 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 and we can find, this is not the scale here, but we can find the amount of energy with respect to units. And let's say this is 10 units. Let me make this a little darker here. 10 units of energy here, you got 20 and 30 and 40 units of energy, etc. So you can see that the reactant started off with about 30 units of energy. I'm just going to call it 30E. And the products ended up with 10E, 10 units of energy. Okay. Now, if we extrapolate where the reactants actually started and go across, we see this hill. On top of the hill is the TS, the transition state. That is where bonds are broken and being made. Remember that picture in the beginning, the transition state. Well, we can do this. We can take that distance between the transition state, and so we got 50, 60, 70, 70 right here, okay? And if we extrapolate, we find the energy value there at 70. So from 70 to 30, 70 to 30, guess what? This is 40 units of energy. Because its topmost height is 70, but it started off at 30. So the difference of where you ended up minus where you started is 40 energy units. So that amount of energy we call the energy of activation, okay? That is the minimum amount of energy necessary to get that reaction from reactant to transition state and go over the hump. After the reaction is done, okay, after the reaction done, the products end up at, say, 10. So we've got 10 energy units. Now that difference between where the products ended versus where they started is a special, we call it the delta H. That's the energy of the reaction. So in this case, it ended up at 10 and it started at 30 units. And so you got 10 minus 30 is negative 20 energy units. The key point is this. It's a negative value because it's always the energy difference between where you ended minus where you started. And you're going to end up with either a positive or negative number. The fact that we ended up with a negative number tells me that this reaction, the way the scale is called exothermic. Remember we talked about exothermic reactions? Those are reactions that give up heat, okay? And this difference here is called delta H. That's the energy of the reaction, all right? And the fact that the energy of the products is much lower than the energy of the reactants tells me that this will be an exothermic reaction and it will get hot, okay? It will give up heat. So there's the key points here is the energy level of where the reactants are, the energy level of where the products are, where we at with the products, okay? The transition states up here, okay? that energy difference between the transition state and where the reactant started is delta E, energy of activation. And that distance from where the products ended up with respect to energy from where they started, we call that delta H, okay? And so we got 1, 2, 3, 4, 5 variables that you should be familiar with. Also, by looking at that reaction, be able to determine whether it's a exothermic or an endothermic reaction. Let me clear this up. So, yeah, okay. The transition state, as I stated, we know that that's the top of the peak there. That is where we're getting a bond-breaking bond formation. Delta H, that's the change of the heat energy. Generally, that's also called the energy of the reaction, is the difference between the energy of the products minus the energy of the reactants. Okay. And if it's an exothermic, because that difference is lower, the products is lower in energy than the reactants, then we have an endothermic. Did I say endothermic reaction? Yeah. Yeah. So my mistake. I got it all back. I was looking at the wrong one. So it's an endothermic reaction when heat enters a reaction. Heat is a reactant. Okay. Exothermic when heat is a product. No, my table is correct. I wrote that correctly up there. That is an example of an exothermic reaction on the top right corner. Okay. This is a reminder about an endothermic versus exothermic, whether heat / energy is either a reactant or a product. Okay. So here in this case, I was not incorrect. It is correct because the energy of the products right here, which if you can do it mathematically and just arbitrarily put some values here, and you say 10 and 20, for example. So it's 10 minus 20, so you end up with negative 10 energy units. The fact that you're negative tells you it is exothermic, okay? Also, you can tell just by visualizing that products is at a lower energy level than reactants were. So again, exothermic reaction. Okay, let me clear this up. Now, with respect to endothermic reaction, it's the opposite. Okay, notice something. The products in this case are higher in energy level than where the reactants were. So, let's say this is 50 and this is, I don't know, call it 10. And so the delta H here will be products, which is 50 minus 10, the reactants. You get a positive number, 40. Okay, so you can do it mathematically if you want by arbitrarily putting units on the y-axis, or you can visualize that the products is at a greater energy level than the reactants were. Okay, and so here you have an endothermic reaction, this diagram. So drawing a diagram or being given a diagram, be able to identify the transition state, where delta H is, the reactants, where the products are, and the energy of activation, okay? Also, you might be able to determine, by looking at it, just determine whether I have a positive or negative delta H. Again, here we have a positive because the energy difference of the products minus the energy difference of the reactants is a positive value. And here's the two diagrams side by side. Notice the top one, which would be exothermic. Okay, this would be an exothermic reaction. We will have a delta H with a negative value. Okay, down here will be an endothermic reaction. The delta H will be a positive value. Okay, this one will get hot. This one will get cold. Okay, and this diagram is simply just a energy profile of a reaction process as it occurs as it goes from reactants to products. Okay, with that being said, I told you it was quick. Oh, almost. I got one more. Sorry. This is the last slide. So with respect to a catalyst, okay, we got a catalyst here. What that is doing is simply reducing the energy of activation. This is the energy of activation, normal, but by adding a catalyst, it reduces that value, okay? So maybe this is, I don't know, 50 units. Down here, maybe it reduce it to be 5 units. So that reaction would go from A to B with a minimum amount of energy, okay? Catalysts are very important. Our intestines, our whole body wouldn't exist, our whole life wouldn't exist without catalysts, because a lot of these reactions that occur in our body, if you try to do them in the test tube without any catalysts, they may never ever react. Okay. All right. So thank God for catalysts. All right, ladies and gentlemen, you are done with 2 chapters here, chapter 10 and chapter 11. And we will begin chapter 12 on Thursday. Okay. All right. Any questions?